Somewhere in this universe, right now, there are stars so massive and so blindingly hot that they are literally blowing themselves apart. Not exploding, not yet. They are still alive, still burning, still fusing elements in their cores. But their own light is so powerful that it is physically shoving their outer layers into space, stripping away mass in violent eruptions that can briefly outshine entire galaxies. These are blue hypergiants, the most extreme stars that can exist. They burn millions of times brighter than our sun. Their surface temperatures can exceed 50,000 degrees, and the terrifying part is, they are not supposed to last. The very physics that makes them so extraordinary is the same physics that ensures they cannot survive for long. Tonight, we are going to find out why. If you find this kind of deep dive into the universe fascinating, a quick like or subscribe really helps the channel out. It's a small thing, but it means more than you know. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, with all that being said, let's begin. Let's start with something fundamental. Something that determines everything about a star before it is even fully formed. Its brightness, its colour, its temperature, its size, how long it will live, and how it will die. That single property is mass. Mass is the most important characteristic any star possesses. If you know how massive a star is, you can predict almost everything else about it. A star with low mass will burn cool and dim and red, living for an extraordinarily long time, potentially trillions of years. A star with high mass will burn hot and bright and blue, dying in just a few million years. Once you understand this relationship, the entire variety of star types begins to make sense. Every star you have ever seen in the night sky, its fate was sealed the moment enough gas collapsed to ignite nuclear fusion in its core. That fate was determined by one thing: how much mass ended up in that collapsing cloud. Our sun is a good starting point because it sits right in the middle of the stellar range. The sun has a surface temperature of about 5,500 degrees Celsius. It shines with a luminosity that we use as our standard measuring stick, 1 solar luminosity. It has a mass of 1 solar mass, which is about 2 nonillion kilograms, a number so large it is meaningless in everyday terms. The sun is classified as a G-type main sequence star, sometimes called a yellow dwarf, and it has been burning steadily for about 4.5 billion years. It will continue burning for roughly another 5 billion years before it begins to die. That gives the sun a total lifespan of roughly 10 billion years. From a human perspective, that seems like forever. And in practical terms, it essentially is. The sun is stable. It is calm. It is predictable. It has been burning hydrogen into helium in its core at a steady rate for billions of years, and it will keep doing so for billions more. This is what a well-behaved star looks like. Moderate mass, moderate temperature, moderate luminosity, and a very long life. But not all stars are this well-behaved. Not by a long stretch. Let's talk about what happens when you start increasing mass. Because here is where the physics become surprising. You might assume that if a star has 10 times the mass of the sun, it should shine about 10 times brighter. That seems logical. More fuel, more energy, more light. But that is not how it works at all. The relationship between a star's mass and its luminosity is not linear. It follows a steep power law. Roughly speaking, luminosity scales with mass to the power of about 3.5. What that means in practice is that a star with 10 times the sun's mass does not shine 10 times brighter. It shines roughly 3,000 times brighter. A star with 50 times the sun's mass shines not 50 times brighter, but somewhere around several 100,000 times brighter. And a star with 100 times the sun's mass can shine more than 1,000,000 times brighter than the sun. These numbers escalate with a ferocity that catches most people off guard. Think about that for a moment. Doubling a star's mass does not double its brightness. It increases the brightness by roughly a factor of about 11. Triple the mass, and the brightness increases by roughly a factor of about 46. This is because more massive stars have higher core temperatures and pressures, which accelerates the rate of nuclear fusion dramatically. The reactions in the core do not just happen a little faster, they happen enormously faster. And the more furiously the star fuses hydrogen into helium, the more energy it produces, and the brighter it shines. But here is the consequence that most people do not expect. Even though more massive stars have vastly more fuel, they burn through that fuel so much faster that they actually live much shorter lives. The sun, with its modest mass, will burn for about 10 billion years. A star with 10 times the sun's mass might live for only about 20 million years. A star with 50 times the sun's mass might live for only about 4 million years. And the most massive stars known, those exceeding 100 solar masses, may live for barely 2 million years. These lifetimes are cosmically tiny. The dinosaurs roamed Earth for over 160 million years. The most massive stars in the universe do not even last 2% of that. They are born, they burn with extraordinary violence, and they die, all in the time it might take for a modest geological change to occur on a planet like Earth. This is the fundamental trade-off of stellar physics. More mass means more power but less time. And the stars we are talking about tonight, blue hypergiants, represent the most extreme version of this trade-off that nature allows. But before we get there, we need to understand the steps below them. The difference between a blue giant, a blue supergiant, and a blue hypergiant is not casual. Each represents a distinct category of stellar extremity. Let's start with color, because color tells you something critical about a star. The color of a star is directly related to its surface temperature. This is basic physics. Any object that is hot enough to glow will emit light, and the color of that light depends on the temperature. Cooler objects glow red, hotter objects glow orange, then yellow, then white, then blue. This is the same reason a flame on a gas stove burns blue at its hottest point and orange or yellow where it is cooler. Stars work the same way, but on a vastly larger scale. Astronomers classify stars by spectral type, using letters that correspond to surface temperature ranges. From hottest to coolest, the sequence goes O, B, A, F, G, K, M. O-type stars are the hottest, exceeding 30,000 degrees Celsius. B-type stars range from about 10,000 to 30,000 degrees. Our Sun, a G-type star, sits in the middle at about 5,500 degrees. M-type stars can have surface temperatures as low as about 2,500 degrees. The key point here is that any star described as blue is a hot star. When astronomers talk about blue giants, blue supergiants, or blue hypergiants, the word blue tells you that the star has a very high surface temperature, typically above 10,000 degrees Celsius, and sometimes far higher. This temperature is not just a number. It reflects what is happening inside the star. The hotter the surface, the more energy is pouring outward from the core. And the more energy pouring outward, the more extreme the conditions inside. The second piece of the classification puzzle is luminosity class. Astronomers also categorize stars by how intrinsically bright they are. Two stars can have exactly the same surface temperature, but vastly different luminosities if one is much larger than the other. A bigger star has more surface area radiating light, so even at the same temperature, it shines brighter. Luminosity class tells you roughly how large and luminous a star is at a given temperature. Main sequence stars, like our Sun, are ordinary stars still in the prime of their lives, steadily fusing hydrogen in their cores. Giants are stars that have evolved off the main sequence and expanded. They are bigger and more luminous. Supergiants are even bigger and more luminous still. And hypergiants, the class we are building toward tonight, sit at the very top of this scale. They are the most luminous stars that exist. When you combine the spectral type with the luminosity class, you get a complete description of where a star sits in what astronomers call the Hertzsprung-Russell diagram, a chart that plots stars by temperature and luminosity. This diagram is one of the most powerful tools in all of astrophysics because it reveals patterns. Most stars fall along a diagonal band called the main sequence, where stars spend the majority of their lives. Giants and supergiants sit above the main sequence because they are more luminous for their temperature, and hypergiants sit at the very top of the diagram, in a region so extreme that very few stars can occupy it. So now, let's walk through the categories. A blue giant is a hot, luminous star, typically with a mass somewhere between about 5 and 15 times the mass of the Sun. Blue giants have surface temperatures in the range of about 10,000 to 30,000 degrees Celsius. They shine anywhere from roughly a few hundred to several thousand times brighter than the Sun. These are impressive stars by any standard. If you replace the Sun with a typical blue giant, Earth would be scorched. The increase in luminosity would make our planet uninhabitable almost immediately. Blue giants are also relatively rare compared to smaller stars. Red dwarfs, the cool, dim stars at the bottom of the mass range, make up about 70% of all stars in the galaxy. Blue giants are far less common because forming a star that massive requires more material and more specific conditions. But even though blue giants are impressive, they are not at the extreme end of the scale. They are hot and luminous, yes, but they can maintain themselves for millions of years. Their mass is high enough to make them remarkable, but not so high that their own energy output begins to threaten their structural integrity. Think of blue giants as powerful athletes, extremely capable, well above average, but operating within limits that their bodies can sustain. Now step up to blue supergiants, and the situation changes significantly. A blue supergiant is a star with a mass typically ranging from about 10 to 50 times the mass of the Sun, though some sit at the higher end of that range and begin to blur the boundary with what comes next. Surface temperatures range from about 10,000 to over 40,000 degrees Celsius, and luminosities can reach anywhere from about 10,000 to several 100,000 times the brightness of the Sun. These are among the most visually spectacular stars in the sky. Rigel, the bright blue-white star that marks the foot of the constellation Orion, is a blue supergiant. It has a mass of roughly 21 times the Sun's mass, a surface temperature of about 12,000 degrees Celsius, and a luminosity of roughly 120,000 times that of the Sun. Rigel is about 860 light-years from Earth, and even at the enormous distance, it is one of the brightest stars in our night sky. If Rigel were at the same distance as Proxima Centauri, our nearest stellar neighbor at about 4.25 light years away, it would be bright enough to cast visible shadows on the ground at night. That is how luminous a blue supergiant is. Blue supergiants burn through their fuel far faster than stars like the Sun. A star like Rigel will not live for billions of years. It will live for maybe 8 to 10 million years total. That sounds like a lot in human terms, but cosmically, it is a blink. These stars are already sprinting toward the end of their lives. They are producing energy at a furious rate, burning through their hydrogen reserves at speeds that would exhaust the Sun's entire fuel supply in a fraction of the time. And because they are burning so fast, they evolve quickly. They change. They do not sit calmly on the main sequence for eons the way the Sun does. They race through evolutionary stages, expanding and contracting, heating and cooling, sometimes in just tens of thousands of years. But even blue supergiants, as extreme as they are, can maintain a kind of equilibrium. They are hot. They are luminous. They are massive. But for the most part, they hold together. Their gravity is strong enough to counterbalance the outward pressure from their enormous energy output. They are pushed, yes. They are strained. But they endure, at least for a while. Now, step up one final level, and everything changes. A blue hypergiant is what happens when a star pushes past the limits of what stellar physics can comfortably sustain. These are stars with masses typically exceeding about 50 solar masses, with some surpassing 100 solar masses or more. Their luminosities are staggering, often exceeding 1 million times the luminosity of the Sun, and in extreme cases reaching 5 million, 6 million, or even higher. Their surface temperatures can range widely depending on their current state, but many sit at 20,000 degrees Celsius or higher, with the hottest reaching 40 or 50,000 degrees. They are, by any measure, the most powerful individual stars in the universe. Let me try to put that luminosity into perspective, because when you hear a number like 1 million times the brightness of the Sun, it can wash over you without really landing. The Sun produces about 386 trillion watts of power every second. That is already an incomprehensible number. Now multiply that by 1 million. A blue hypergiant with a luminosity of 1 million solar luminosities is radiating roughly 386 billion trillion watts. It is producing more energy every single second than most stars produce in hours or days. If you placed a blue hypergiant where the Sun is, Earth would not just be scorched, it would not just be sterilized. The sheer flood of energy would overwhelm everything. The radiation pressure alone, the physical push of light itself, would be immense. And that radiation pressure, as we will explore in depth shortly, is not just a side effect. It is one of the defining forces shaping these stars. Blue hypergiants are also enormous in physical size. Because they are so luminous and so hot, their outer layers extend outward to vast radii. Some blue hypergiants have radii dozens of times larger than the Sun's, making them physically immense. Not as large as the most bloated red supergiants like Betelgeuse, which sacrifice the temperature for sheer size, but still enormous by any standard. The combination of extreme temperature and extreme size gives blue hypergiants their extraordinary luminosity. The amount of energy a star radiates depends on two things: its surface temperature and its surface area. Both of these are extreme in blue hypergiants, and the combination produces a luminosity that is almost unmatched anywhere in the universe. The critical thing to understand, and this is the idea that anchors everything we are going to discuss tonight, is that blue hypergiants are not simply bigger versions of blue supergiants. They are qualitatively different. There is a threshold of mass and luminosity beyond which a star's behavior fundamentally changes. Below that threshold, a star can be hot and bright and still maintain a reasonable equilibrium. Its gravity holds it together. Its energy flows outward in an orderly fashion. The star is powerful, yes, but it is stable. Above that threshold, everything breaks down. The energy output becomes so extreme that radiation itself begins to compete with gravity for control of the star. The outward push of photons, the individual particles of light streaming out from the core, becomes powerful enough to physically shove the star's outer layers into space. The star does not just shine, it tears itself apart from the inside, not in a single catastrophic explosion, but in a slow, violent, grinding process that strips mass away over thousands of years. This is what defines a blue hypergiant. It is not simply a very massive, very hot star. It is a star that has crossed a line, a star whose own luminosity has become a weapon against its own existence. It is a star in a state of war with itself, gravity pulling inward, radiation pushing outward, and neither side fully winning. The result is chaos, violent mass loss, extreme instability, eruptions, and a rapidly changing structure that shifts on timescales that are shockingly short by stellar standards. And this is exactly why blue hypergiants are so rare. Not just because you need an enormous amount of mass to create one, though that alone makes them uncommon, but because the state itself is inherently temporary. Stars cannot remain blue hypergiants for long. The forces at work inside them are so extreme that the star is constantly evolving, constantly losing mass, constantly being reshaped by its own energy output. A blue hypergiant is not a stable destination. It is a phase, a brief and violent chapter in the life of the most massive stars. They pass through it. They cannot linger. To appreciate just how rare these stars are, consider the numbers. The Milky Way contains somewhere between 100 billion and 400 billion stars. Of those, only a tiny fraction, perhaps a few tens of thousands, are massive enough to be classified as blue supergiants. And of those few tens of thousands, an even smaller number qualify as blue hypergiants. We know of perhaps a few dozen candidates in our entire galaxy. Some estimates are even lower. That means for every blue hypergiant in the Milky Way, there may be 10 billion or more ordinary stars. You could search through an entire galaxy and barely find a handful. This rarity is not accidental. It is a direct consequence of how stars form. Stars condense from collapsing clouds of gas and dust called molecular clouds. The physics of this collapse tends to favor the formation of smaller stars. Low-mass stars like red dwarfs form far more easily and far more frequently than high-mass stars. The distribution of stellar masses, what astronomers call the initial mass function, drops off steeply at higher masses. For every star born with 50 or more solar masses, thousands of smaller stars are born. The universe simply does not produce many stars this massive, and the few that are produced burn so fast and evolve so quickly that at any given moment, even fewer are caught in the blue hypergiant phase. Think of it this way. If the life of a sun-like star is a long, steady novel spanning hundreds of pages, the life of a blue hypergiant is a single burning page torn from the middle of a much shorter book. The hypergiant phase itself may last only a few tens of thousands of years, perhaps less, out of a total stellar lifetime that may be only 2 or 3 million years. In cosmic terms, that is almost nothing. You would have to be looking at exactly the right time and exactly the right place to catch a star in this extreme state. So where do you actually find them? Blue hypergiants do not appear randomly scattered across a galaxy. They are almost exclusively found in regions where massive star formation has occurred recently, because they live and die so quickly that they never have time to wander far from where they were born. This means young, massive star clusters and active star-forming regions, the kinds of places where enormous clouds of molecular hydrogen have recently collapsed under their own gravity, fragmenting into hundreds or thousands of new stars, a few of which accumulated enough mass to become the extreme objects we are talking about tonight. If you could somehow visit one of these regions, what you would see would be staggering. Imagine approaching a young star cluster in which a blue hypergiant resides. From a distance of a few light years, the star would dominate everything. You would not need a telescope. You would not need to search for it. It would be the single most overwhelmingly bright object in your field of view, blazing with a blue-white intensity that dwarfs every other star in the cluster around it. Its light would be so rich in ultraviolet radiation that it would be ionizing the surrounding gas for light years in every direction, carving out a vast glowing bubble of heated hydrogen called an H2 region. The nebula around it would glow in vivid pinks and reds and purples, sculpted by the star's radiation and stellar wind into arcs and pillars and filaments. The star itself, if you could look at it without being blinded, would appear intensely blue-white, far more vivid than any star visible from Earth's night sky. Surrounding the blue hypergiant, you would likely see the shells and rings of material it has already ejected, expanding outward like the layers of an onion, each one a record of a past eruption or an era of particularly intense stellar wind. Closer in, the wind itself would be visible as a faint glow of ionized gas streaming outward from the star's surface at thousands of kilometers per second, a constant hemorrhage of mass that you could actually see if you had the right instruments. This is not a calm corner of space. This is one of the most energetic environments in the galaxy. And the blue hypergiant at its center is the engine driving all of it, pouring energy into its surroundings on a scale that reshapes the interstellar medium for light years around. It is not just a star, it is an event. And yet, despite their rarity and their brevity, blue hypergiants are among the most important stars in the universe. They influence their surroundings on scales that far exceed their physical size. Their intense ultraviolet radiation ionizes vast regions of interstellar gas, creating enormous glowing nebulae around them. Their powerful stellar winds carry material outward at speeds of hundreds or even thousands of kilometers per second, enriching the surrounding space with heavy elements forged in their cores. When they finally die, as they must, they do not go quietly. They produce some of the most powerful explosions in the universe, seeding space with the elements that will eventually form the next generation of stars and planets. Everything about a blue hypergiant, its mass, its luminosity, its temperature, its instability, its violent mass loss, its brief and furious existence, all of it traces back to one thing: mass. Mass is the engine that drives a star's luminosity. Luminosity is the force that drives its instability. Instability is the process that drives its mass loss. And mass loss is the mechanism that determines how quickly the star evolves and ultimately how it dies. It all connects. Every extreme property of a blue hypergiant is a downstream consequence of having been born with an extraordinary amount of mass. This is the foundation we need to build on. Because now that we understand what a blue hypergiant is, now that we can see it clearly as a physically distinct and incredibly extreme class of star, separated from ordinary blue giants and blue supergiants by more than just size, but by a fundamental shift in how the star behaves, we need to look more closely at the engine that makes them so violent. We need to understand why this much luminosity is not just impressive, but dangerous. Why it does not just make the star bright, but makes it inherently, unavoidably, physically unstable. We need to understand radiation pressure, the Eddington limit, and the invisible war being fought inside every blue hypergiant between the force of gravity and the raw power of light itself. We have established what a blue hypergiant is. We know it is a star of extraordinary mass, extraordinary temperature, and extraordinary luminosity. We know it is rare, brief, and violent. But now, we need to go deeper. We need to understand the engine that drives all of this extremity, because the story of a blue hypergiant is not really a story about size. It is a story about power. Specifically, it is a story about what happens when a star produces so much energy that its own light becomes a structural force, one powerful enough to rival gravity itself. And to understand that, we need to look closely at the physics that links mass, luminosity, and the invisible pressure of radiation. Let's begin with a question that sounds simple, but has a profound answer. Why do more massive stars shine so much brighter? We touched on this earlier, but now let's really explore the mechanism, because the answer reveals why blue hypergiants are not just impressive stars, but fundamentally unstable ones. In any star, the energy that produces light and heat comes from nuclear fusion in the core. In a star like the Sun, the dominant process is called the proton-proton chain, or PP chain. This is a series of nuclear reactions in which hydrogen nuclei, individual protons, fuse together step by step to create helium. Each reaction releases a tiny amount of energy. But the Sun's core contains an enormous number of protons, and trillions upon trillions of these reactions happen every second. The cumulative result is the steady outpouring of energy that we see as sunlight. The Sun converts about 600 million tons of hydrogen into helium every second. That is a staggering number, but the Sun has so much hydrogen that it can sustain this for about 10 billion years. Now, in more massive stars, the core temperature and pressure are much higher. And at these higher temperatures, a different and far more efficient fusion process takes over. It is called the CNO cycle, which stands for carbon, nitrogen, oxygen. In this process, carbon atoms act as a catalyst, facilitating the fusion of hydrogen into helium at a much faster rate than the PP chain. The CNO cycle is extraordinarily sensitive to temperature. Its energy output scales with temperature to roughly the 16th power. That means even a modest increase in core temperature produces a dramatic increase in energy output. A star with a core that is just twice as hot as the Sun's core does not produce twice as much energy. It produces roughly 65,000 times as much energy from the CNO cycle alone. This is the key to understanding why massive stars are so luminous. Their higher mass creates higher gravitational pressure in the core, which creates higher temperatures, which triggers the CNO cycle, which generates energy at a rate that escalates wildly with every additional increment of mass. The relationship between mass and luminosity is not gentle, it is violent. It is a steep curve that climbs faster and faster the more massive the star becomes. For stars on the main sequence, this relationship can be approximated as luminosity being proportional to mass raised to the power of roughly 3.5. To illustrate this with different examples, a star with 15 times the sun's mass does not shine 15 times brighter. It shines roughly 12,000 times brighter. A star with 60 times the sun's mass reaches well over 1 million times the sun's luminosity. And for the most extreme cases, above about 80 solar masses, the luminosity can climb to several million solar luminosities, though the simple power law begins to break down as the star approaches its Eddington limit. These are not gentle increases, these are explosive escalations. Each doubling of mass multiplies the luminosity by roughly a factor of 11. The curve gets steeper and steeper, meaning that at the highest masses, even small additions of material produce enormous increases in energy output. Now here is where this becomes critical for understanding blue hypergiants. All of that energy, all of those photons being generated in the core at that furious rate, they have to get out. They have to travel from the core through the star's interior and eventually escape from the surface. And as those photons stream outward, they interact with matter. They collide with atoms, with electrons, with ions in the star's interior. And every time a photon collides with a particle of matter, it transfers a tiny amount of momentum. It gives the particle a tiny push outward. This is radiation pressure. It is the physical force exerted by light. In everyday life, radiation pressure is so weak that you never notice it. The sunlight falling on your hand exerts a pressure on your skin, but it is so faint that you would need extraordinarily sensitive instruments to measure it. But inside a star, the situation is completely different. The radiation field is not gentle warmth. It is an inferno of photons, unimaginably dense and energetic, streaming outward from a core where temperatures reach tens of millions of degrees. And in the most massive stars, this radiation field becomes so intense that the outward pressure it exerts begins to compete with the inward pull of gravity. Think about what this means. In a star like the Sun, gravity wins easily. The outward pressure from radiation and thermal energy balances gravity, but gravity is comfortably in control. The Sun is in a stable equilibrium called hydrostatic equilibrium. It does not expand, it does not contract. It just sits there, burning steadily, held in a comfortable balance between two opposing forces. This equilibrium is robust. If something perturbed the Sun slightly, if it expanded a little, gravity would pull it back. If it contracted a little, the increased pressure would push it back out. The Sun self-corrects. It is stable. But as you increase a star's mass and therefore its luminosity, the radiation pressure component grows faster than gravity does. Gravity increases linearly with mass. If you double the mass, you double the gravitational pull. That is a straightforward, proportional increase. But luminosity does not follow that gentle rule. It obeys a power law, climbing as mass to the roughly 3.5 power. So while gravitational force merely doubles or triples, with each corresponding increase in mass, the luminosity leaps upward by factors of 10 or 50 or more. The gap between them widens at every step. The radiation pressure is climbing far faster than gravity can keep up. This means that in more massive stars, the balance between gravity and radiation pressure becomes increasingly precarious. The star is still in equilibrium, technically. Gravity and pressure still balance, but the margin is thinner. The star is closer to the edge. A smaller perturbation could upset the balance, and the star's ability to self-correct, to restore equilibrium after a disturbance, becomes weaker. Now, there is a theoretical limit to this. A boundary beyond which radiation pressure would actually exceed gravity, and the star could no longer hold itself together. This limit was first described by the British astrophysicist Sir Arthur Eddington in the 1920s, and it is called the Eddington limit, or sometimes the Eddington luminosity. The Eddington limit is the maximum luminosity a star of a given mass can have while still maintaining hydrostatic equilibrium. At the Eddington limit, the outward force of radiation pressure on the star's outer layers exactly equals the inward force of gravity. If the star's luminosity were to exceed the Eddington limit, radiation pressure would overwhelm gravity, and the outer layers of the star would be blown outward into space. The star would literally begin to push itself apart. The Eddington limit depends on the star's mass. More massive stars have stronger gravity, so they can tolerate higher luminosities before reaching the limit. But here's the problem. As we have just seen, luminosity increases with mass far more steeply than gravity does, so even though more massive stars have a higher Eddington limit, their actual luminosity climbs toward that limit faster. The result is that the most massive stars live dangerously close to their Eddington limits. They are producing so much energy that their own radiation pressure is almost as strong as their gravity. They are balanced, but barely. Like a ball sitting on top of a hill rather than in a valley. Technically stable, but only just. Blue hypergiants are the stars that live closest to this edge. Their luminosities often approach 90% or more of their Eddington limit. Some may even temporarily exceed it during certain phases of their evolution. And this proximity to the Eddington limit is what makes them so fundamentally different from less massive stars. It is what transforms them from merely bright and hot into genuinely unstable. Let me give you a concrete comparison to help you feel the difference. Consider our sun. The sun's luminosity is roughly 1 solar luminosity by definition. The Eddington limit for a star of the sun's mass is about 33,000 solar luminosities. That means the sun is shining at about 1/33,000th of its Eddington limit. It is nowhere near the edge. Radiation pressure in the sun is a minor player. Gravity dominates completely. The sun could increase its energy output by a factor of 30,000 before radiation pressure would even begin to threaten its structural integrity. The sun is safe. It is not going anywhere. Now consider a blue hypergiant with 100 solar masses. Its Eddington luminosity might be roughly 3 million solar luminosities, and its actual luminosity might be somewhere between 1 million and 2 million solar luminosities. That means it is shining at perhaps 30 to 70% of its Eddington limit. Some blue hypergiants in certain evolutionary phases may approach 80 or 90%. The margin between the star's actual energy output and the point where radiation would tear it apart has shrunk from a factor of 30,000 to a factor of less than 2. The star is not comfortably balanced. It is walking a tightrope. And here is what makes the situation even more precarious. The Eddington limit is not a sharp line. It is not like a cliff edge where you are either safely standing on solid ground or falling. It is more like a slope that gets steeper and more slippery the closer you get. As a star approaches its Eddington limit, its outer layers become increasingly loosely bound. The gravitational hold on those outer layers weakens relative to the outward push of radiation. The layers begin to puff up, to expand. The star becomes physically larger and more diffuse. And as the outer layers become more tenuous, they become more susceptible to instabilities, to perturbations, to being ejected into space by even minor fluctuations in the star's energy output. This is not a theoretical abstraction. We can observe the consequences directly. Blue hypergiants have some of the most powerful stellar winds in the universe. A stellar wind is a continuous flow of material from a star's surface into space, driven primarily by radiation pressure. Our sun has a solar wind, a gentle breeze of charged particles streaming outward at speeds of a few hundred kilometers per second. The sun's mass loss rate from its solar wind is tiny, roughly 100 trillionth of a solar mass per year. At that rate, the sun would need to blow for trillions of years to lose even a noticeable fraction of its mass. Blue hypergiants are a completely different story. Their stellar winds can carry material outward at speeds of 1,000 to 3,000 kilometers per second, and their mass loss rates are staggering. A blue hypergiant can lose mass at a rate of roughly 100,000th to 1/10,000th of a solar mass per year. That might not sound like much, but remember, these stars only live for a few million years total. At a mass loss rate of 1/10,000th of a solar mass per year, a star would lose an entire solar mass, the equivalent of our entire sun, in just 10,000 years. Over the course of a blue hypergiant's life, it can lose tens of solar masses through its wind alone. It is hemorrhaging material into space at a rate that would be inconceivable for a star like the sun. And the wind is not even the most dramatic form of mass loss. Blue hypergiants can also undergo giant eruptions, episodes where the star suddenly brightens dramatically and expels enormous quantities of mass in a short period. During one of these eruptions, a blue hypergiant can eject several solar masses of material in just years or decades. These eruptions are among the most energetic events a star can produce, short of a supernova. They create expanding shells and nebulae of gas around the star, visible evidence of the violent history of mass loss that defines these objects. What drives these winds and eruptions? Radiation pressure. The same force we have been discussing. The photons streaming outward from the core interact with the atoms in the star's outer layers, particularly with the electrons in ionized metals like iron. Iron has many energy levels and therefore many opportunities to absorb and re-emit photons. Each absorption event transfers momentum from the photon to the atom, pushing the atom outward. In the dense, luminous environment of a blue hypergiant's atmosphere, this process is relentless. Billions upon billions of photons, each one delivering a tiny kick to the particles in their path, collectively driving a river of matter outward from the star's surface. The Stefan Boltzmann law tells us that the total energy radiated by a star depends on both its surface temperature and its surface area. For blue hypergiants, both of these quantities are large. The temperature is high, often 20,000 to 40,000 degrees Celsius or more. And the surface area is enormous, because these stars, despite being called blue, are physically immense. The combination produces a luminosity that floods the star's outer atmosphere with photons. And those photons do not simply pass through. They interact, they push, they drive material outward with a relentless, tireless force. There's also a subtlety here that makes the situation even more complex. radiation pressure does not affect all parts of the star equally. Deep inside the star, where the density is very high, photons interact so frequently with matter that they cannot travel far before being absorbed and re-emitted. The radiation field is trapped, bouncing around in the dense interior, slowly diffusing outward over thousands of years. In this deep interior, the radiation pressure is enormous, but it is balanced by the equally enormous gravitational pressure. The system is in equilibrium, though a tense one. But as you move outward toward the star's surface, the density drops. Photons can travel farther between interactions. The radiation begins to flow more freely. And in the outermost layers of the star, where the density is lowest, the radiation pressure can become dominant over gravity. These outer layers are the most vulnerable. They are the least tightly bound by gravity and the most strongly pushed by radiation. This is where the stellar wind originates. This is where eruptions begin. The star's surface is the battleground where the war between gravity and radiation is most openly fought. In less massive stars, gravity wins this battle easily. The surface layers are firmly held in place. There is a gentle solar wind, yes, but the mass loss is negligible. The star's structure is secure. In blue hypergiants, the battle is nearly even. Gravity holds the star together, but only just. The surface layers are loosely bound, bloated, and puffed up by radiation pressure. Even small fluctuations in the star's energy output can tip the balance locally, causing bursts of enhanced mass loss or triggering instabilities that propagate through the outer layers. The star is constantly on the edge, constantly adjusting, constantly losing material, constantly evolving, and this brings us to one of the most important concepts in understanding why blue hypergiants behave the way they do. It is not enough to simply say that the star is close to its Eddington limit. The real issue is that being close to the Eddington limit makes the star exquisitely sensitive to perturbations. In a stable star like the Sun, small disturbances are damped out. If a bubble of gas rises slightly, it cools, becomes denser, and sinks back down. If a region compresses slightly, the increased pressure pushes it back out. The star self-corrects constantly, maintaining its equilibrium through negative feedback loops. In a blue hypergiant near the Eddington limit, those feedback loops weaken or even reverse. A small increase in luminosity, caused perhaps by a slight fluctuation in the fusion rate in the core, increases the radiation pressure on the outer layers. This causes the outer layers to expand slightly. As they expand, they become less dense, which can actually increase the efficiency of radiation pressure on them, because photons can push them more easily. This causes them to expand more, which makes them even more susceptible to radiation pressure and so on. Instead of negative feedback that restores equilibrium, you get positive feedback that amplifies the disturbance. Small perturbations grow rather than shrink. This is the fundamental reason why blue hypergiants are unstable. They exist in a regime where the normal self-correcting mechanisms of stellar structure begin to fail. The star cannot settle into a calm, steady state because every minor fluctuation has the potential to grow into a significant disturbance. The star oscillates, pulsates, erupts, and sheds mass not because something unusual is happening to it from the outside, but because the internal physics of its own extreme luminosity prevents it from ever truly being at rest. There is another factor that amplifies this instability. There is another consequence of extreme mass loss that makes the situation progressively worse. The fusion reactions that generate the star's luminosity occur deep in the core. The core's conditions, its temperature, its pressure, its density, are determined by the weight of the material above it. When mass is lost from the surface, the core does not immediately respond. It keeps burning at roughly the same ferocious rate. This creates a growing mismatch. The surface gravity weakens as mass is stripped away, but the luminosity pouring outward from the core remains largely unchanged. The star becomes less able to hold itself together even as the force trying to push it apart stays constant. The ratio of luminosity to gravitational binding shifts further and further toward radiation pressure with every passing century of mass loss. What this means in practical terms is that blue hypergiants do not simply burn through their fuel and then die. They are actively eroding from the outside while burning from the inside. The surface is being stripped, the core is being exhausted. Both processes work on timescales that are extraordinarily short by stellar standards, and both push the star away from the blue hypergiant state. The star's own power is not just impressive, it is corrosive. It is eating the star alive. A blue hypergiant might start its life with 100 solar masses, but by the time it reaches its final evolutionary stages, it might have only 30 or 40 solar masses remaining. The rest has been thrown into space, blown away by the star's own light. Some of the most dramatic examples of this process are the stars known as luminous blue variables, or LBVs. These are massive stars, many of which are blue hypergiants or closely related to them, that undergo spectacular episodes of variability and mass loss. An LBV can brighten by 1 or 2 magnitudes over months or years, swell in size, cool dramatically, and then return to its previous state. During these outbursts, the star can eject enormous quantities of material, creating expanding shells and nebulae that surround the star like the layers of an onion. Consider Eta Carinae, one of the most massive and luminous stars known in our galaxy, located about 7,500 light-years from Earth. With a luminosity estimated at roughly 5 million times that of the Sun, Eta Carinae sits extraordinarily close to its Eddington limit, and the consequences are written across the sky around it. This star has undergone catastrophic eruptions in recorded human history. Events where radiation pressure in its outer layers overwhelmed gravity and enormous quantities of mass were hurled into space. These were not nuclear explosions. The core did not collapse. The star did not die. Instead, radiation pressure simply won its battle against gravity in the outermost layers, and the star's own light physically shoved its own material outward at hundreds of kilometers per second. The star lost mass equivalent to several entire suns in a matter of years, not because of some external catastrophe, but because its own energy output exceeded what its gravity could contain. We will explore the specifics of these extraordinary eruptions more closely as our story continues. But the critical point right now is the mechanism. This is radiation pressure in action at its most extreme. This is what happens when a star's luminosity pushes past the boundary that gravity can enforce. The star does not gently shed a breeze of particles the way the sun does. It hemorrhages, it convulses, and it does so because the physics at this level of luminosity leaves it no other option. P Cygni, a blue hypergiant in the constellation Cygnus, about 5,000 to 6,000 light-years from Earth, provides another example. P Cygni underwent a massive eruption in 1600. suddenly appearing as a naked eye star where none had been seen before, then fading over subsequent decades. The material ejected during that eruption formed a nebula around the star that is still visible today. P Cygni now shines at a luminosity of roughly 500,000 to 600,000 times that of the Sun, placing it firmly in the blue hypergiant category. Its spectrum shows characteristic features of powerful mass loss, with strong emission lines indicating a dense, fast-moving stellar wind. These examples show what happens when a star lives near its Eddington limit. The star does not simply sit and burn, it erupts, it sheds mass, it brightens and dims unpredictably. It reshapes itself over timescales that are breathtakingly short by astronomical standards, years, decades, centuries, instead of the millions or billions of years that characterize the evolution of more modest stars. And there is something else we need to understand about the physics of these stars. The opacity of the material in the star's outer layers plays a crucial role in determining how strongly radiation pressure acts. Opacity is a measure of how effectively a material blocks or absorbs light. High opacity means photons interact frequently with matter, transferring more momentum, creating more radiation pressure. Low opacity means photons pass through more freely, exerting less pressure. In the outer layers of blue hypergiants, opacity is dominated by the interactions between photons and metal ions, particularly iron. Iron is especially important because it has a complex atomic structure with many energy levels, giving it many opportunities to absorb photons. At temperatures around 150,000 to 200,000 degrees Celsius in the stellar interior, iron ions undergo a sharp increase in opacity. This creates what astrophysicists call an opacity bump, a region in the star where the material suddenly becomes much more effective at blocking and absorbing radiation. This opacity bump acts like a dam in a river. Radiation flowing outward from the core encounters this region of enhanced opacity and is partially blocked. The energy builds up behind the opacity bump, increasing the local radiation pressure. This can destabilize the layers above, causing them to expand, pulsate, or be ejected. Many of the instabilities observed in blue hypergiants and luminous blue variables are thought to be connected to these opacity-driven effects in their interiors. The combination of extreme luminosity, proximity to the Eddington limit, opacity-driven instabilities, and the positive feedback loops we discussed earlier creates a situation where the star is perpetually out of equilibrium in its outer layers. The core may be relatively stable, quietly fusing hydrogen or heavier elements, but the envelope, the vast outer region of the star, is a chaotic, turbulent, ever-changing environment. Material is constantly being pushed outward, heated, accelerated, and in many cases ejected entirely from the star. This is why astrophysicists sometimes describe blue hypergiants as living on the edge. Not metaphorically, literally. They exist at the boundary of what is physically possible for a star. Any more luminous and they would blow themselves apart entirely. Any less massive and they would settle into a more stable state. They occupy a narrow band in the Hertzsprung-Russell diagram, where the forces governing stellar structure are almost perfectly matched, creating a fundamentally unstable and dynamic object. And this inherent instability has consequences that extend far beyond the star itself. The material ejected by blue hypergiants doesn't simply vanish. It forms massive circumstellar nebulae, expanding shells and rings of gas and dust that can extend for light years around the star. These nebulae are rich in heavy elements synthesized in the star's interior. Elements like carbon, nitrogen, oxygen, and heavier metals that were dredged up from the core by the star's violent convective motions and then ejected into space by radiation-driven winds and eruptions. When the star eventually dies, whether in a supernova or some other terminal event, these surrounding nebulae interact with the explosion, shaping its appearance and influencing the distribution of elements into the interstellar medium. The mass that a blue hypergiant sheds during its lifetime does not disappear. It becomes part of the raw material for the next generation of stars and planets. In a very real sense, the instability of blue hypergiants is one of the engines that drives the chemical evolution of galaxies. So let's bring this together. The physics of blue hypergiants can be summarized in a single chain of causation. Extreme mass produces extreme core temperatures. Extreme core temperatures trigger the CNO cycle at furious rates. The CNO cycle produces extreme luminosity. Extreme luminosity creates extreme radiation pressure. Extreme radiation pressure approaches the Eddington limit. Proximity to the Eddington limit creates fundamental instability. Instability drives violent mass loss through winds and eruptions, and that mass loss reshapes the star on timescales that are shockingly brief. Every link in this chain follows inevitably from the one before it. There is no step where the star could choose a different path. There is no configuration where a star this massive could burn quietly and calmly the way the sun does. The physics does not allow it. From the moment a star accumulates enough mass to become a blue hypergiant, it is locked into a path of extreme luminosity, extreme instability, and extreme mass loss. The star's own power is the source of its undoing. And this raises the question that defines the next stage of our journey. If blue hypergiants are inherently unstable, if they cannot maintain equilibrium, if they are constantly losing mass and constantly evolving, then how long can a star actually remain in this state? What happens as it continues to shed material? Where does the star go from here? And why do astrophysicists say that stars are not supposed to stay this extreme? Now we arrive at the heart of what makes blue hypergiants so extraordinary and so tragic. We have seen what they are. We have explored the physics that makes them so luminous and so powerful. But here is the question we have been building toward. If these stars are so extreme, if their own luminosity is constantly fighting against their gravity, if their outer layers are perpetually on the verge of being blown into space, then how long can they actually remain in this state? The answer is not long. Not long at all, and the reason is not just that they burn through their fuel quickly, though they do. The reason is deeper than that. The state itself, the condition of being a blue hypergiant, is physically unsustainable. The star's own properties work against its continued existence in this form. It is not merely burning fast, it is actively dismantling itself, shedding the very mass that defines it, evolving away from its own extreme state on timescales that are shockingly brief by any astronomical standard. To understand why, we need to talk about a boundary that was discovered not through theory alone, but through careful observation. In the late 1970s and early 1980s, two astronomers at the University of Minnesota, Roberta Humphreys and Chris Davidson, undertook a systematic study of the most luminous stars in our galaxy and in nearby galaxies. They plotted these stars on the Hertzsprung-Russell diagram. the chart that maps stars by surface temperature and luminosity, and they noticed something remarkable. There was a region in the upper part of the diagram that was conspicuously empty. You would expect that if very massive stars can exist across a range of temperatures, you would find extremely luminous stars at all temperatures. Hot blue stars, warm yellow stars, cool red stars, all at very high luminosities. But Humphreys and Davidson found that this is not the case. Above a certain luminosity, roughly 500,000 to 600,000 times the luminosity of the Sun, there are almost no stable stars at intermediate temperatures. You can find extremely luminous blue stars, and you can find extremely luminous red supergiants, but the region in between the yellow and warm zones of the diagram at the highest luminosities is essentially forbidden territory. This empty zone is now called the Humphreys-Davidson limit, and it represents one of the most important empirical boundaries in stellar astrophysics. Stars do not simply avoid this region by coincidence. They are physically prevented from occupying it for any sustained period. When a massive star tries to cross into this region, when it attempts to evolve from a hot blue state toward a cooler yellow or red state at extreme luminosities, it encounters catastrophic instability. Its outer layers, already loosely bound by the marginal balance between gravity and radiation pressure, become violently unstable. The star erupts, it ejects mass, it throws off enormous shells of material, and these eruptions prevent the star from making the transition smoothly. The star either sheds enough mass to drop below the critical luminosity threshold, allowing it to continue evolving, or it oscillates wildly near the boundary, brightening and fading, swelling and contracting, trapped in a cycle of instability that can last for centuries or millennia. This is the behavior we observe in luminous blue variables, or LBVs. These stars, many of which are blue hypergiants or closely related to them, are caught in precisely this trap. They sit near the Humphreys-Davidson limit and undergo dramatic episodes of variability. During quiescent phases, an LBV might appear as a hot blue star with a surface temperature of 20,000 to 30,000 degrees Celsius. Then, over months or years, it brightens, cools, and swells, its surface temperature dropping to perhaps 8,000 or 9,000 degrees, while its visual brightness increases dramatically. The star appears to be moving towards the forbidden zone, but it cannot stay there. The instability intensifies, mass is ejected violently, and eventually the star contracts and heats back up, returning to a hotter, bluer state. Then, the cycle begins again. What is happening here is extraordinary. The star is not simply pulsating like a heartbeat. It is trying to evolve, trying to move across the Hertzsprung-Russell diagram as its internal structure changes, and failing. The physics of its own extreme luminosity will not allow it to cross smoothly into cooler temperature regimes at these high luminosities. Every time it tries, radiation pressure in the expanding outer layers triggers instability, mass loss accelerates, and the star is forced back. It is like watching something try to walk through a wall and being repelled every time. The timescales involved are remarkable. LBV eruptions can last years to decades. The intervals between major eruptions can be centuries, and the entire LBV phase in a massive star's life might last only a few tens of thousands of years. That sounds like a long time in human terms, but for a star, it is astonishingly brief. The sun has been burning for 4.5 billion years. A blue hypergiant might spend only 30,000 years in its LBV phase, before evolving into something else, That is less than 100,000th of the Sun's current age. Let me walk through what an LBV eruption actually looks like, because these events are amongst the most dramatic phenomena in stellar astrophysics. During a major LBV eruption, the star can increase its visual brightness by 1 to 2 magnitudes or more, becoming several times to many times brighter as seen from Earth. The outer layers swell and the surface temperature drops. The star appears to shift from blue to yellow or even to orange-white, but the total energy output across all wavelengths often stays roughly constant or increases only modestly. What changes dramatically is how that energy is distributed. As the star expands and cools, the peak of its radiation shifts from the ultraviolet into the visible spectrum. The star appears much brighter to our eyes, even though its total energy output may not have changed as much as the visual brightening suggests. But during the most extreme eruptions, something more violent happens. The star does not merely expand and cool, it actually exceeds its Eddington limit, at least locally and temporarily. Radiation pressure overwhelms gravity in the outer layers, and enormous quantities of mass are ejected. We are not talking about a gentle increase in the stellar wind. We are talking about entire solar masses of material being hurled into space in single events lasting years or decades. The most famous example remains Eta Carinae and its great eruption of the 1840s. During that event, the star ejected an estimated 10 to 40 solar masses of material. The ejector formed the Homunculus Nebula, a spectacular bipolar structure about 1 light-year across that is expanding outward at speeds of roughly 650 kilometers per second. The energy released during the Great Eruption was extraordinary. For a brief period, Eta Carinae radiated energy at a rate comparable to a supernova, yet the star survived. This has led some astrophysicists to classify events like this as supernova imposters, events that mimic the brightness of a supernova, but leave the star intact. How is it possible for a star to release this much energy and survive? The answer lies in the mechanism. A supernova involves the catastrophic collapse and explosion of the star's core. It is terminal. The star is destroyed. An LBV eruption, even an extreme one, involves the ejection of the star's outer layers, not the destruction of its core. The core remains intact, still fusing elements, still generating energy. It is the envelope, the vast outer region of the star, that is being violently disrupted and partially expelled. The star loses a significant fraction of its mass, but its nuclear engine keeps running. After the Great Eruption, Eta Carinae faded from naked eye visibility. It continued to shed mass through a powerful stellar wind and underwent a smaller eruption in the 1890s. Today, Eta Carinae remains one of the most luminous stars in our galaxy, shining at roughly 5 million times the luminosity of the Sun. It is still surrounded by the expanding debris of its past eruptions, and it is almost certainly still unstable. Many astrophysicists believe that Eta Carinae could undergo another major eruption or could explode as a supernova in the relatively near future. Though near future in astronomical terms could mean any time in the next several 100,000 years. A G Carinae is another LBV that illustrates this behavior beautifully. Located roughly 20,000 light-years from Earth, A.G. Carinae has a luminosity of about 1 million to 1.5 million times that of the Sun. It has undergone multiple recorded outbursts over the past century, each time brightening and cooling before returning to a hotter state. A G Carinae is surrounded by a ring nebula composed of material the star has ejected over the past 10,000 years or so. A visible fossil record of repeated eruptions. This nebula is a physical record of the star's violent history, layer upon layer of expelled material marking eruption after eruption, each one stripping away more of the star's mass. Doradus, the prototypical LBV and the star for which an entire class of variable stars was originally named, sits in the Large Magellanic Cloud about 160,000 light-years away. Doradus has a luminosity of roughly 1 million solar luminosities and undergoes variations of 1 to 2 magnitudes over timescales of years to decades. It represents the classic LBV behavior, a star trapped near the Humphreys-Davidson limit, oscillating between hotter and cooler states, unable to settle, constantly shedding mass. What all these examples show us is that the LBV phase is not a stable configuration. It is a crisis. The star's core is evolving, burning through its fuel, pushing it to move across the Hertzsprung-Russell diagram. But its extreme luminosity creates a barrier that prevents smooth evolution. The result is a stuttering, violent, eruptive passage through the most extreme regions of the diagram, marked by dramatic mass loss at every step. Now, let's talk about what all this mass loss actually means for the star's evolution, because this is where the title of tonight's exploration comes into focus. Stars are not supposed to stay this extreme, and the reason is that the mass loss itself changes the star. Every solar mass ejected into space is a solar mass of gravitational binding that the star has lost. With less mass, the star has less gravity. With less gravity, the Eddington limit drops. With a lower Eddington limit, the star's existing luminosity pushes it even closer to the edge, or even over it. This drives even more mass loss, which reduces the mass further, which lowers the Eddington limit further, and the cycle continues. This is a self-reinforcing process. The star cannot stop it. The very act of losing mass makes future mass loss more likely and more severe. Each eruption makes the next one easier to trigger. Each decade of strong stellar wind shaves away more material, weakening the star's gravitational hold on what remains. The star is caught in a downward spiral, peeling away its own layers, evolving rapidly away from the blue hypergiant state because it physically cannot sustain it. The timescale of this evolution is breathtaking. While a star like the Sun changes imperceptibly over millions of years, a blue hypergiant can transform visibly over human timescales. Eta Carinae has changed dramatically in just the past 2 centuries. P. Tigni has changed over the past 4 centuries. These are not ancient, unchanging beacons. They are evolving before our eyes. Where does the star go as it loses mass? There are several possibilities, and the specific path depends on the star's initial mass, its metallicity, the details of its mass loss history, and factors that are still not fully understood. One common evolutionary pathway takes the star from the blue hypergiant phase through the LBV phase, and eventually into a Wolf-Rayet star. Wolf-Rayet stars are a class of extremely hot, luminous stars that have been stripped of their outer hydrogen envelopes, exposing the products of nuclear fusion at their surfaces. A Wolf-Rayet star is essentially the bare core of what was once a much more massive star. Its outer layers, the hydrogen-rich envelope that once surrounded it, have been blown away by the relentless mass loss that defines the blue hypergiant and LBV phases. Wolf-Rayet stars are extraordinary objects in their own right. They have surface temperatures exceeding 50,000 degrees Celsius, sometimes reaching over 100,000 degrees. They have powerful stellar winds that carry material outward at speeds of 1,000 to 5,000 kilometers per second. They are highly luminous, though less luminous than the blue hypergiants they evolved from, because they have lost so much mass. In a sense, Wolf-Rayet stars are the skeletons of blue hypergiants, what remains after the star has shed its outer layers and exposed its nuclear-processed interior. The transition from blue hypergiant to Wolf-Rayet star is not always smooth. It can involve additional eruptions, further episodes of extreme mass loss, and dramatic changes in the star's appearance. Some stars may pass back and forth between LBV-like states and Wolf-Rayet-like states as they evolve. The boundaries between these categories are not always sharp, and individual stars can defy easy classification. But the direction of evolution is clear. The star is losing mass. It is moving from a state of extreme bloated instability toward a more compact, stripped-down state. The blue hypergiant phase is a waypoint, not a destination. It is a stage the star passes through on its way to something else, and that passage is driven by the fundamental incompatibility between the star's extreme luminosity and its ability to hold itself together. Another aspect of why stars cannot remain blue hypergiants for long is the relentless pace of nuclear evolution in their cores. These stars are not just losing mass from their surfaces, they are simultaneously burning through their nuclear fuel at an extraordinary rate. A blue hypergiant might fuse hydrogen in its core for only a few million years. Once the hydrogen is exhausted, the core contracts, heats up, and begins fusing helium. Helium burning lasts a fraction of the time hydrogen burning did, perhaps a few 100,000 years. Then, the core exhausts its helium and begins fusing carbon. Carbon burning might last only a few thousand years, then neon burning, lasting perhaps a year, then oxygen burning, lasting months, then silicon burning, lasting only about a day. Each successive stage of nuclear burning is shorter than the last, because each fuel produces less energy per reaction, and the core requires ever higher temperatures and pressures to sustain fusion. The star is racing through its nuclear fuel supply at an accelerating pace, each stage briefer and more desperate than the one before. While the surface is erupting and shedding mass, the core is undergoing its own rapid transformation, building up an ever heavier core of nuclear ash that will eventually determine the star's ultimate fate. This dual acceleration, mass loss stripping the exterior while nuclear burning races through the interior, means that the blue hypergiant phase is squeezed from both directions. The star cannot remain in this state for long, because its surface is being blown away and its core is evolving rapidly beneath it. The combination of these two processes ensures that the blue hypergiant phase is one of the shortest-lived stages in stellar evolution. A star might spend a few million years on the main sequence as a hot blue star, but it might spend only tens of thousands of years, or even less, as a blue hypergiant before evolving into something else. Let me put this in perspective with some numbers that illustrate just how rapid this evolution is. Consider a star born with roughly 100 solar masses. On the main sequence, it burns hydrogen steadily for about 2 to 3 million years. During this time, it is a massive, luminous O-type star, hot and bright but relatively stable. Then it evolves off the main sequence and enters the blue supergiant and blue hypergiant phase. This phase might last only 50,000 to 100,000 years. During this time, it might lose 20 to 40 solar masses through winds and eruptions. Then it transitions to a Wolf-Rayet star and spends perhaps another 200,000 to 500,000 years in that state, continuing to lose mass, and then, with its core exhausted, it explodes. The blue hypergiant phase, the period of maximum instability and most extreme behavior, occupies perhaps 2 to 5% of the star's total lifetime. If the star's life is a 2-hour movie, the blue hypergiant phase is about 3 to 5 minutes of screen time. It is a brief, violent chapter in an already short story. And this brevity is not a coincidence. It is a direct consequence of the physics we have been discussing. The star cannot remain a blue hypergiant for longer than this, because the mass loss rate is too high. Every year, every decade, every century, the star is losing mass. And as it loses mass, it moves away from the conditions that define a blue hypergiant. It either loses enough mass to become a Wolf-Rayet star, or its core evolves to the point where the star's surface properties change dramatically. Either way, the blue hypergiant state is a transient phenomenon. A star passes through it. It does not remain. This is why astronomers know so few blue hypergiants. It is not just that massive stars are rare to begin with, though they are. It is that even among massive stars, the blue hypergiant phase is so short-lived that catching a star in this state requires extraordinary timing. If you survey the Milky Way and find 400 billion stars, perhaps a few tens of thousands are massive enough to ever become blue hypergiants. But of those tens of thousands, only a handful are in the blue hypergiant phase right now, at this particular moment in cosmic history. The rest have either not yet reached this stage, or have already passed through it and evolved into something else. There's also an important observational challenge. Blue hypergiants are often surrounded by the dense circumstellar material they have ejected. This material can obscure the star, absorb its light, and re-emit it at longer wavelengths. Some blue hypergiants may be hidden behind their own debris, invisible at optical wavelengths, detectable only in the infrared. The star AFGL 2298, for example, is believed to be an LBV or blue hypergiant candidate, but it is so deeply embedded in its own ejected material that it is essentially invisible in optical light. We know it is there only because of its infrared signature. There may be other blue hypergiants in our galaxy that we have not yet identified, because they are hidden behind walls of their own expelled matter. The mass that blue hypergiants eject does not simply disappear into the void. It forms spectacular structures around the star, circumstellar nebulae that can persist for thousands or tens of thousands of years before dispersing into the interstellar medium. These nebulae are rich in the products of nuclear burning that have been dredged up from the star's interior by convective mixing. Nitrogen, carbon, helium, and heavier elements are enriched in these ejecta compared to the surrounding interstellar gas. When this material eventually mixes into the broader interstellar medium, it contributes to the chemical enrichment of the galaxy, providing raw materials for the next generation of stars and planets. Some of these circumstellar nebulae are among the most beautiful objects in the sky. The ejecta surrounding Eta Carinae, which we already discussed, glow in reflected starlight and thermal emission, sculpted into intricate shapes by the forces that expelled them. But other examples are equally striking. The ring nebula around A.G. Carinae is a nearly circular shell of ejected material, roughly 5 light years in diameter, that traces the history of the star's mass loss over millennia. These nebulae are not just beautiful, they are scientific records, frozen evidence of the star's violent past, allowing astronomers to reconstruct the history of eruptions and mass loss that shape the star. The presence of these nebulae also shapes what happens when the star finally dies. A blue hypergiant does not explode into a clean vacuum. It explodes into the graveyard of its own past, into layers and shells and clouds of material that has spent thousands of years ejecting. All of that debris is still out there when the end comes. And when the final explosion arrives, it does not simply pass through that material as though it were not there. It collides with it. And the consequences of that collision are extraordinary. But that is a story that belongs to the star's death, and we will get there soon enough. For now, the critical point is this. The nebulae that surround blue hypergiants are not just beautiful remnants. They are active participants in the star's ultimate fate, shaped by the same mass loss that defined the star's life, and destined to play a role in its final moments. This brings us to an important realization about the nature of blue hypergiants. Everything about them, their luminosity, their temperature, their mass loss, their instability, their variability, their circumstellar nebulae, all of it is connected. None of these properties exists in isolation. Each one drives and is driven by the others in a web of interconnected physical processes. The star's luminosity drives its mass loss. The mass loss changes its luminosity and its gravitational binding. The changing balance between gravity and radiation pressure drives instability. The instability drives eruptions. The eruptions create the nebulae. The nebulae influence the star's eventual death. It is a single, unified story of a star pushed to its limits by its own power, constantly evolving, constantly changing, unable to rest in any one configuration for more than a brief moment by cosmic standards. And this is ultimately what the title means. Stars are not supposed to stay this extreme. Not because it is forbidden by some cosmic law, not because it is literally impossible, but because the physics of extreme mass and extreme luminosity creates conditions that are inherently temporary. The very forces that make a blue hypergiant so spectacular are the same forces that ensure it cannot last. Radiation pressure strips away mass. Mass loss weakens gravity. Weakened gravity makes further mass loss easier. The core races through its fuel. The star evolves rapidly away from the conditions that defined it. The blue hypergiant state is self-terminating. It carries within it the seeds of its own end. No star can fight this. No amount of mass can overcome the fundamental instability created by extreme luminosity near the Eddington limit. No configuration of temperature and pressure can keep the outer layers stable when the radiation field is this intense. The star will lose mass. It will evolve. It will change. And eventually it will reach a point where it is no longer a blue hypergiant at all, either because it has shed enough mass to become something else, or because its core has evolved to the point where its surface properties change, or because the core finally collapses and the star explodes. The blue hypergiant phase is a fire that burns too hot to sustain itself. It is a state that exists precisely because nature can create stars this massive, but cannot make them stable at this level of power. And that tension between creation and destruction, between the ability to form these extraordinary objects and the impossibility of maintaining them, is one of the most beautiful and revealing paradoxes in all of astrophysics. It tells us something deep about the universe. The most powerful things in it are often the most fragile. The brightest stars are the ones that cannot last. We have followed the blue hypergiant from its birth as an extraordinarily massive star through the physics that makes it so luminous and so violent, and through the instabilities and mass loss that ensure it cannot remain in this extreme state for long. Now we arrive at the final question. How does it end? What happens to a star that has spent its brief and furious existence burning millions of times brighter than the sun, shedding enormous quantities of mass, erupting and reforming, evolving at a pace that defies the usual timescales of stellar life? The answer is that it dies. And it dies spectacularly, in one of the most powerful events the universe can produce. But the details of that death, the specific pathway a blue hypergiant follows to its end, depend on factors that are still not fully understood. Some of those pathways are well established by decades of observation and theory. Others remain genuinely uncertain, the subject of active research and ongoing debate. And that uncertainty is itself part of the story, because blue hypergiants push our understanding of stellar physics to its limits. Let's start with what we know. The core of a blue hypergiant, despite all the chaos happening at the surface, has been following its own relentless trajectory the entire time. While the outer layers erupted and shed mass and oscillated in temperature, the core was quietly racing through the same accelerating sequence of nuclear fuels we traced earlier, each stage shorter and more desperate than the last. What took millions of years at the beginning now takes months, then days. The core has reached its final fuel. By the time it finishes burning silicon, the end is very close. Silicon fuses into iron 56, the final product that stellar fusion can produce efficiently. And iron 56 is a dead end. Fusing it further does not release energy. It absorbs energy. When the core has been converted entirely to iron, there is no more nuclear fuel to burn. There is nothing left to generate the outward pressure that has been holding the core up against gravity for millions of years. What happens next takes less than a second. The iron core, no longer supported by the outward pressure of fusion, collapses under its own gravity. The collapse is catastrophic and nearly instantaneous. The core falls inward at speeds approaching a quarter of the speed of light. In less than a second, a core that was roughly the size of Earth is compressed into a sphere perhaps 12 miles across. The density of this compressed core is so extreme that a teaspoon of it would weigh billions of tons. The material is compressed to the density of an atomic nucleus, a state where protons and electrons are forced together to form neutrons. The result is a neutron star, one of the most extreme objects in the universe. The collapse releases an almost inconceivable amount of gravitational energy. Most of it, roughly 99%, is carried away by neutrinos, ghostly subatomic particles that barely interact with matter. The remaining 1% powers the explosion that follows. A shockwave rebounds off the newly formed neutron star and plows outward through the remaining layers, tearing through the star at tens of thousands of kilometers per second. It heats the material to billions of degrees, triggering a final burst of nuclear fusion in the expanding debris. The outer layers of the star are blown outward into space in a catastrophic explosion. This is a core collapse supernova. A core collapse supernova is one of the most energetic events in the universe. For a few weeks, A single exploding star can outshine an entire galaxy containing hundreds of billions of stars. The explosion releases roughly 10 to the 46 joules of energy in neutrinos alone, with roughly 10 to the 44 joules going into the kinetic energy of the expanding debris in the light we actually see. The expanding shell of material, enriched with heavy elements forged in the star's core and in the explosion itself, plows outward into the surrounding interstellar medium at thousands of kilometers per second. Over thousands of years, this material mixes with the interstellar gas, contributing the heavy elements that will eventually be incorporated into new stars, new planets, and potentially new life. For a blue hypergiant, the supernova is even more dramatic because of all the material the star has previously ejected. Remember those massive eruptions and powerful stellar winds that stripped tens of solar masses from the star over the preceding millennia? That material is still out there, expanding outward from the star but still relatively close in cosmic terms. When the supernova blast wave reaches this circumstellar material, it slams into it at tremendous speed. The collision converts kinetic energy into radiation, producing intense light across the electromagnetic spectrum. The supernova brightens dramatically, often far more than it would if the star had exploded into empty space. Some of the most luminous supernovae ever observed are thought to be precisely this type of event: a massive star that shed enormous quantities of mass before exploding, so that the blast wave interacted violently with the surrounding debris. SN 2006 GY is one of the most famous examples. Discovered in the galaxy NGC 1260, this supernova was extraordinarily luminous, roughly 100 times brighter than a typical supernova at its peak. It remained bright for an unusually long time, shining for months before fading. The most widely accepted explanation is that the progenitor star, likely a massive LBV or blue hypergiant, had ejected many solar masses of material in eruptions shortly before the explosion. The supernova blast wave collided with this dense circumstellar shell, converting enormous amounts of kinetic energy into light. The result was a supernova of extraordinary brightness, powered not just by the explosion itself, but by the violent interaction between the blast and the star's own previously expelled matter. SN 2009 IP is another fascinating case, and one that highlights the uncertainty that still surrounds these objects. This event, detected in a spiral galaxy roughly 70 million light-years away, was initially classified as a supernova imposter, a giant eruption of an LBV similar to Eta Carinae's Great Eruption. The star had been observed to brighten and fade multiple times in the years leading up to the main event, behavior consistent with LBV variability. Then, in 2012, a much brighter event occurred, one that many astronomers interpreted as a true supernova. But the classification remains debated. Some researchers argue that even the 2012 event was another imposter, an extremely energetic eruption that the star survived. Others believe it was a genuine core collapse. The star has not been clearly detected since, which supports the supernova interpretation, but the debate continues. This case illustrates how difficult it can be to distinguish between a massive LBV eruption and a true supernova, and how much we still have to learn about the final stages of these extreme stars. There is also the historical case of SN 1961 Vivi, an event observed in a galaxy about 30 million light-years away. For decades, astronomers debated whether this was a supernova or a supernova imposter. The star was apparently an extremely massive and luminous blue star before the event. After the brightening, a faint source remained visible at the location, which some interpreted as the surviving star and others interpreted as a compact remnant or echo. This case has never been fully resolved, and it remains one of the most puzzling events in the study of massive star death. These ambiguous cases reveal something important. The boundary between an extreme LBV eruption and a true supernova is not always clear-cut. Both involve enormous releases of energy. Both can eject large quantities of mass. Both can produce temporarily brilliant brightening visible across millions of light years. The difference is that a supernova destroys the star's core, while an eruption leaves it intact. But from a distance of millions of light years, distinguishing between these two outcomes can be extremely difficult, especially when the star is embedded in dense circumstellar material that complicates the observations. Now, core collapse supernovae are not the only possible end for a blue hypergiant. For the most massive stars, those born with initial masses exceeding roughly 130 solar masses, there is another possibility that is even more extreme. These stars may undergo what is called a pair instability supernova. In a pair instability supernova, the core reaches such extreme temperatures, exceeding about 1 billion degrees Celsius, that the photons in the core begin to spontaneously convert into pairs of matter and antimatter particles, specifically electron-positron pairs. This process removes photon pressure from the core because the photons that were providing outward support are being converted into particles. The sudden drop in radiation pressure causes the core to contract rapidly. The contraction heats the core further, which triggers a runaway thermonuclear explosion. Unlike a core collapse supernova, where the explosion is driven by the rebound off a neutron star, a pair instability supernova is a thermonuclear detonation of the entire core. The explosion is so powerful that it completely destroys the star, leaving no remnant behind. No neutron star, no black hole, nothing. The star is obliterated entirely, its material scattered into space. Pair instability supernovae are expected to be extraordinarily luminous, potentially tens to hundreds of times brighter than ordinary supernovae. They would eject enormous quantities of heavy elements into the surrounding medium. But they are also expected to be extremely rare, because only the most massive stars, those that retain enough mass in their cores despite all the surface mass loss, can reach the conditions necessary to trigger pair instability. And as we have discussed, blue hypergiants lose mass at prodigious rates. A star born with 150 solar masses might have only 50 or 60 solar masses remaining by the time it approaches core collapse. Whether it retains enough mass in its core to undergo pair instability depends on the details of its mass loss history, which can vary enormously from star to star. At the other extreme, some blue hypergiants may die not with the spectacular explosion, but with an eerie quiet. If the star's core is massive enough, roughly above about 40 to 50 solar masses at the time of collapse, though this threshold is uncertain and model dependent, the core may collapse directly into a black hole without producing a bright supernova at all. This is sometimes called a failed supernova or direct collapse. In a failed supernova, the collapsing core forms a black hole so quickly that the shock wave that would normally power the explosion never fully develops, or proves too weak to propagate outward through the massive overlying layers. The star simply vanishes. One moment it is there, shining fiercely, The next, it is gone, replaced by a black hole that quietly swallows whatever material remains. There may be a faint transient as some outer layers fall inward, but nothing like a normal supernova. The star goes out not with a bang, but with something closer to a whisper. This is a genuinely unsettling possibility, and there is some observational evidence for it. Surveys monitoring large numbers of massive stars have identified a few candidates where a luminous star appears to have simply disappeared without producing a bright supernova. One of the best known candidates is a massive red supergiant in a nearby galaxy that vanished from observations around 2015 without a clear supernova detection. While red supergiants and blue hypergiants are different types of stars, the underlying mechanism, direct collapse of a massive core into a black hole, could apply to either. There is also the possibility that some blue hypergiants could produce gamma-ray bursts, the most energetic explosions in the universe. Long-duration gamma-ray bursts, those lasting more than about 2 seconds, are thought to be produced by the collapse of rapidly rotating massive stars. In the collapsor model, a massive star's core collapses to form a black hole, and material falling into the black hole forms an accretion disk that launches 2 narrow, extremely energetic jets outward along the rotation axis. If one of these jets happens to be pointed toward Earth, we observe it as a gamma-ray burst, a brief flash of high-energy radiation that can outshine the rest of the observable universe for a few seconds. Not all blue hypergiants will produce gamma-ray bursts. The progenitor star needs to be rapidly rotating and to have lost most of its hydrogen envelope, so that the jets can punch through the remaining material. Stars that have evolved through the LBV phase and lost their envelopes, transitioning into Wolf-Rayet states, are considered the most likely progenitors. But the connection between blue hypergiants, LBVs, Wolf-Rayet stars, and gamma-ray burst progenitors is still an active area of research. The evolutionary pathways are complex, and individual stars may follow different trajectories depending on their mass, rotation, metallicity, and binary interactions. Speaking of binary interactions, this is an important factor that adds yet another layer of complexity. Many massive stars exist in binary systems, orbiting a companion star. Gravitational interactions with a companion can dramatically alter a star's evolution. Mass can be transferred from one star to the other. Tidal forces can spin the star up or slow it down. In extreme cases, the two stars can merge, creating a single star of exceptional mass that might not have formed through normal channels. Some blue hypergiants may owe their extreme mass not to being born extraordinarily massive, but to having gained mass through a merger or mass transfer from a companion. If so, their evolutionary pathways could differ significantly from those of single stars of the same mass. HD 5980 is a compelling example. Located in the small Magellanic Cloud about 200,000 light-years from Earth, HD 5980 is a massive binary system containing at least one star that has exhibited LBV-like eruptions. The interactions between the two stars in this system have complicated efforts to understand the evolutionary state of either component. Binary systems like this remind us that the clean, simple picture of a single star evolving through well-defined phases is an idealization. Reality is messier. Many massive stars have companions, and those companions influence how the star lives and how it dies. Let me also mention some specific blue hypergiant candidates to give you a sense of the variety that exists among these extreme objects. The Pistol star, located near the center of our galaxy about 25,000 light years from Earth, was once considered one of the most luminous stars known, with a luminosity estimated at up to 10 million times that of the Sun. Subsequent observations have revised this estimate downward, but the Pistol star remains extraordinarily luminous, probably in the range of 1 million to several million solar luminosities. It is surrounded by the Pistol Nebula, a massive shell of ejected gas that the star expelled roughly 4,000 to 6,000 years ago. The Pistol star is a prime example of a blue hypergiant that has undergone significant mass loss and is likely in a transitional evolutionary phase. R136 AI1, located in the Large Magellanic Cloud, is one of the most massive stars ever discovered. Earlier estimates placed its mass as high as 300 solar masses, but more recent analyses have revised this to roughly 170 to 250 solar masses, though significant uncertainty remains. Its luminosity is estimated at roughly 4 to 6 million times that of the Sun. R136 AI1 is so extreme that it challenges our models of stellar evolution. Stars this massive were not predicted to be stable by earlier theoretical models, and their existence has forced astrophysicists to revise their understanding of how the most massive stars form, leave, and die. R136 AI1 is classified as a WNH star, a type of Wolf-Rayet star that still retains some hydrogen on its surface. It may represent a star in the process of transitioning from the blue hypergiant phase to a fully stripped Wolf-Rayet state, or it may be something we do not yet have an adequate category for. BATE 9998, also in the Large Magellanic Cloud, is another extraordinarily luminous and massive star with a luminosity approaching 5 million solar luminosities. Like R136A1, it challenges the boundaries of our stellar models and blurs the lines between traditional classification categories. What makes these stars so compelling is not just the numbers, not just the extraordinary luminosities and masses we can assign to them from a distance. It is what we can actually observe when we train our best instruments on them. When astronomers examine the spectrum of a star like the Pistol star, they see something very different from the clean, well-ordered absorption lines of a calm star like the Sun. The spectrum is dominated by powerful emission lines, bright spikes of light at specific wavelengths that indicate dense, fast-moving gas streaming away from the star's surface. Hydrogen emission lines are broadened and distorted by the Doppler effect, revealing that material is flowing outward at speeds exceeding several hundred kilometers per second, simultaneously in multiple directions. Helium and nitrogen lines appear unusually strong, evidence that nuclear processed material from deep inside the star has been dredged to the surface by violent convective motions and is now being expelled into space. The spectrum does not look like that of a normal star. It looks like a record of chaos, a fingerprint of a star in turmoil. When astronomers image the nebulae surrounding these stars, the story deepens further. The Pistol Nebula, for example, is not a smooth, uniform shell. It has structure, clumps, arcs, and asymmetries that reveal the history of the star's mass loss was not steady or symmetrical. Some regions of the nebula are denser than others, suggesting that certain eruptions were more violent or more directional than others. The nebula contains roughly 10 solar masses of material, all of it expelled from the star in a period of perhaps 4,000 to 6,000 years. That is an average mass loss rate that is extraordinary by any standard, but the uneven structure tells us the actual loss was probably episodic, occurring in bursts rather than as a smooth, continuous flow. R136 AI1 presents its own observational puzzles. It sits at the center of the R136 cluster in the Tarantula Nebula, a massive star-forming region in the Large Magellanic Cloud. The cluster is so densely packed with hot, luminous stars that separating R136 AA1 from its neighbors requires extremely high-resolution observations. Only with the Hubble Space Telescope, and more recently with adaptive optics on large ground-based telescopes, have astronomers been able to isolate the star and measure its properties individually. Even then, the measurements carry significant uncertainty. Determining the mass of a star this extreme requires careful modeling of its spectrum, its luminosity, and its wind properties, and different models can give different answers. Current best estimates place R136 AI1 somewhere between 170 and 250 solar masses. Though these figures have already been revised downward from earlier higher values, and may shift again as methods improve, the star is so far beyond the range of anything we can study in a laboratory or even simulate with complete confidence in a computer that every measurement is pushing the limits of our methods. These are not abstract theoretical objects. They are real stars being studied right now by real astronomers using the most powerful telescopes humanity has ever built. And they continue to surprise us. These individual examples illustrate an important point. While we understand the broad outlines of blue hypergiant physics, the evolution of mass, luminosity, and instability that we have been discussing throughout this story, the details for individual stars can be surprising, contradictory, and difficult to reconcile with theory. Astrophysics is not a finished science. It is a work in progress. And blue hypergiants, sitting at the extreme edge of what stars can be, are precisely the objects where our models are most likely to fail or to reveal gaps in our understanding. What is well established is clear. Blue hypergiants are the most massive, most luminous stars that exist. Their extreme luminosity places them near the Eddington limit, creating fundamental instability. This instability drives violent mass loss through winds and eruptions. The mass loss ensures that the blue hypergiant phase is brief, a transient state that no star can maintain for more than a few tens of thousands of years. And at the end of this brief, violent chapter, the star dies, either in a supernova, a hypernova, a pair instability supernova, a gamma ray burst, or a direct collapse into a black hole. What remains uncertain is equally important. We do not fully know the precise mass thresholds that determine which death pathway a given star follows. We do not know exactly how much mass is lost during the LBV phase and how much survives to influence the final explosion. We do not know whether pair instability supernovae have actually been observed or only theorized. We do not know the role of binary companions in shaping the evolution and death of blue hypergiants. We do not know whether some blue hypergiants might cycle through multiple LBV-like phases before dying, or whether the transition to a Wolf-Rayet state is always a one-way journey. These are open questions, and they are among the most actively studied topics in modern astrophysics. But let's step back from the technical details for a moment and think about what blue hypergiants mean in the broader context of the universe. These stars are, in a very real sense, the universe's most dramatic acts of creation and destruction combined. They are the most powerful furnaces in existence, forging heavy elements in their cores at a pace that dwarfs anything smaller stars can achieve. The carbon, nitrogen, oxygen, silicon, and iron that they produce and ultimately scatter into space are the raw materials from which new stars and planets form. The calcium in your bones, the iron in your blood, the oxygen you breathe, these atoms were forged in the cores of massive stars and distributed into space by exactly the kinds of violent events we have been describing tonight. Blue hypergiants are among the most important contributors to the chemical enrichment of galaxies. Without stars this massive, the universe would contain far fewer heavy elements, and rocky planets like Earth might be far rarer or might not exist at all. There's something deeply poetic about this. The most unstable, the most violent, the most extreme stars in the universe are also among the most essential. Their very instability is what makes them so important. If they burned calmly and quietly, they would hold their heavy elements inside, locked away in a stellar core that would never share its riches with the rest of the cosmos. But because they are unstable, because their radiation pressure strips their outer layers into space, because they erupt and shed mass and ultimately explode, they seed the universe with the elements that make complexity possible. The violence is not incidental, it is functional. It is the mechanism by which the universe distributes the building blocks of everything we know. And so we arrive at the central paradox we set out to explore. Blue hypergiants are stars that are not supposed to stay this extreme. Their own power ensures that they cannot. The radiation pressure that makes them so luminous is the same force that tears them apart. The mass that makes them so gravitationally powerful is the same mass that fuels a luminosity too great to be contained. They exist in a state of perpetual crisis, burning too bright, losing mass too fast, evolving too quickly, always on the edge of destruction. And yet, the universe keeps making them. Massive molecular clouds keep collapsing. New stars of extreme mass keep forming, and those stars keep burning their way into the blue hypergiant phase, even though that phase is guaranteed to be brief. Nature does not avoid extremes, it explores them. It pushes matter and energy to their limits, and then lets the physics play out. Blue hypergiants are what happens when that exploration reaches the very edge of what a star can be. They are magnificent and terrifying and doomed all at once. They are the universe's way of testing its own boundaries, finding out how bright, how hot, how massive, how powerful a single object can become before it destroys itself. The next time you look up at the night sky, consider this. Somewhere out there, right now, a star is burning millions of times brighter than the sun. Its outer layers are being shoved into space by its own light. Its core is racing through its fuel at a pace that leaves it only thousands of years before collapse. It is losing mass, erupting, oscillating, trapped in a state that physics will not allow it to sustain. It is one of the rarest and most extraordinary objects in the entire cosmos, and it will not last. Nothing that extreme ever does, but while it burns, it is glorious. And when it finally dies, whether in a supernova that briefly outshines 1 billion suns, or in a quiet collapse that leaves only darkness behind, it will scatter its atoms across space. Those atoms will drift for millions of years. They will mix into clouds of gas and dust. They will collapse into new stars and new planets. And some of them, perhaps, will find their way into a small rocky world orbiting a calm yellow star, where they will become part of the soil, the water, the air, and eventually part of something that can look up at the sky and wonder where it all came from. That is the legacy of a blue hypergiant. Not permanence, contribution, not stability, transformation, not a long, quiet life, but a short and brilliant one that changes the universe forever. And that is enough. That is more than enough. Thank you for joining me on this journey tonight. If this exploration meant something to you, a like or a subscribe would mean a great deal. It helps me keep making these deep dives into the most extraordinary things the universe has to offer. The cosmos is full of wonders, and blue hypergiants are among the greatest. They burn too hot, they shine too bright, and they cannot last. But while they exist, there is nothing else like them in all of creation. Sleep well tonight. And if you happen to look up at the stars, remember that a few of them, just a handful in all the galaxy, are burning with a power that the universe itself can barely contain. Good night.